Think about the night sky, those countless specks of light you see when you look up. Now, imagine that everything visible to your eyes, every star and galaxy, is just a tiny fraction of what's actually out there. Beyond what we can observe lies a realm so vast and mysterious, it challenges everything we think we know about the universe. This is the cosmic frontier, the edge of everything, where the rules of physics twist into the unknown, and reality itself seems to unravel. And today, we're diving headfirst into 30 of its most baffling secrets. Picture standing on the shore of an endless ocean, staring at the horizon. You know there's more beyond it, but the details are hidden, shrouded in waves and mist. The edge of the universe is like that, except instead of water, it's woven from dark energy, invisible forces, and phenomena so strange they sound like science fiction. Somewhere out there, space might be stretching faster than light can travel, galaxies could be vanishing into voids we can't explain, and what lies beyond the observable universe. The truth is, we don't know, but every mystery we uncover at the edge pulls us closer to answering the biggest question of all: what is the universe really made of? This journey isn't just about distant stars or cold, empty space, it's about pushing the limits of human understanding. Each of these 30 enigmas is a piece of a puzzle that could redefine reality as we know it. From ghostly particles that pass through you unnoticed to colossal walls of galaxies spanning billions of light years, the cosmos is stranger than anything we've ever imagined. And the most thrilling part, we're just getting started. So if you've ever wondered what hides in the shadows of the universe, where the laws of physics break down, and whether we're truly alone in the void, stick around. What you're about to discover will change how you see the night sky forever. Somewhere out there in the darkness, an invisible force is tugging at our galaxy along with thousands of others, like a cosmic puppeteer. This is the Great Attractor, one of the universe's most perplexing mysteries. Hidden behind the dense stars and dust of the Milky Way's galactic plane, it exerts a gravitational pull so immense that entire galaxy clusters are being drawn toward it at staggering speeds of hundreds of kilometers per second. Yet for decades we couldn't even see what was causing it. The discovery came in the 1970s, when astronomers noticed something strange. Galaxies in our local supercluster weren't moving randomly. Instead, they were all streaming toward a single point in space, as if caught in a celestial current. The problem: that exact spot was obscured by our own galaxy's bulge, making it nearly impossible to observe directly. Even today, with advanced telescopes peering through the galactic haze, the Great Attractor remains shrouded in mystery. Current estimates suggest it has the mass of tens of thousands of Milky Ways clustered together, but what exactly makes up that mind-boggling concentration of matter? Some theories point to an enormous supercluster of galaxies, while others suggest something even stranger: a confluence of dark energy, or perhaps a vast concentration of the invisible dark matter that permeates the cosmos. There's even speculation that the Great Attractor might not be the final destination, that an even larger structure, nicknamed the Shapley supercluster, could be pulling everything toward it from beyond. One thing's certain: unraveling this cosmic riddle could rewrite our understanding of gravity itself. After all, how does something we can barely see command the motion of the universe on such an unimaginable scale? But what if the Great Attractor isn't the only invisible force steering the cosmos? Astronomers have discovered something even more bizarre: a mysterious current dragging entire galaxy clusters in the same direction, like leaves caught in a cosmic river. They call it dark flow, and it shouldn't exist. According to everything we know, the universe expands evenly in all directions after the Big Bang, carrying galaxies along with it. But in 2008, researchers studying the movement of over 1,000 galaxy clusters noticed something unsettling. These colossal structures weren't just drifting apart, they were also being pulled toward a single point outside the observable universe, as if some unimaginably vast structure beyond our cosmic horizon was tugging on them. The speed, a staggering 1,000 kilometers per second, the implications are staggering. If dark flow is real, it suggests there's something out there, something so massive, it warps the fabric of spacetime on a scale we've never seen. Maybe it's a supercluster of galaxies so enormous it dwarfs anything in our visible universe. Maybe it's a remnant of an earlier cosmic epoch, a relic from before the Big Bang. Some theorists even speculate it could be evidence of a parallel universe exerting gravitational influence on our own. Here's what makes dark flow so unsettling. It defies the cosmological principle, the idea that the universe should look roughly the same in every direction. If galaxy clusters are all streaming toward one unseen attractor, it means the cosmos might be far more lopsided and far stranger than we ever imagined. And the most chilling possibility, whatever's causing this flow could be so distant, its light will never reach us. We might be forever in the dark about what lies beyond the edge. So how do you explain the inexplicable? That's the dilemma astronomers face. Some argue dark flow is just an illusion, a quirk of incomplete data. Others believe it's the first clue to a reality we've barely begun to grasp. One thing's clear, if this cosmic current is real, it's rewriting the rules of the universe and our place within it. Now picture a hole in the universe so vast you could drop 1,000 Milky Ways into it and still have room to spare. This is the Boötes void, a staggering cosmic desert stretching 330 million light-years across, where galaxies should be packed shoulder to shoulder. Astronomers found almost nothing. It's like stumbling upon a city where every building has vanished, leaving only a few scattered lampposts glowing in the dark. Discovered in the 1980s during galaxy surveys, the void defies all expectations. In a region where scientists predicted around 2,000 galaxies, they counted fewer than 60. That's 99.9% empty space. To put it in perspective, if our Milky Way were floating in the Boötes void, we wouldn't have discovered another galaxy until the 1960s, because the nearest one would be millions of light-years away. So how does something this enormous and empty even exist? One theory suggests it's the aftermath of ancient cosmic titans, superclusters of galaxies that merged long ago, their gravitational dance flinging matter outward like debris from a collision. Another idea points to the influence of dark energy, stretching space so rapidly in this region that galaxies couldn't hold together, leaving behind a ghostly bubble. But the most mind-bending hypothesis, that the void is evidence of an advanced civilization so unfathomably old, they've harnessed the energy of entire galaxies, leaving behind a dark, engineered footprint. What makes the Boötes void so unsettling isn't just its size, it's how it exposes gaps in our cosmic maps. According to standard models, matter should be distributed more evenly across the universe. Finding a void this colossal is like realizing the ocean has a bottomless trench no one predicted. Some researchers argue it's a statistical fluke, a rare but natural emptiness. Others whisper it might be a glitch in reality itself, a sign we're missing something fundamental about how the universe stitches itself together. Here's the twist, even this near-perfect void isn't entirely empty. Those few galaxies stranded inside it behave strangely. Some are oddly young, as if they formed late in cosmic history. Others seem stretched and warped, their light stretched into redder wavelengths, hinting they're being pulled toward something we can't see. It's as if the void is hiding secrets in its very emptiness, whispering questions we're only beginning to hear. If the universe is a tapestry, the Boötes void is a thread pulled loose, unraveling assumptions about how matter clusters and space evolves. Every time we point telescopes at this cosmic nothingness, we're confronted with the same humbling truth: the edge of understanding isn't just far away, it's full of holes. Right now, as you watch this, our entire galaxy is drifting through what scientists call the KBC void, a bubble of relative nothingness so large it makes you question whether the universe is playing tricks on us. Named after astronomers Keenan, Barger, and Cowie, who identified it in 2013, this cosmic emptiness stretches over 2 billion light-years across, making the Boötes void seem like a pothole in comparison. But here's the catch: we're inside it. That's right, the Milky Way, along with our neighboring galaxies, sits in this sprawling underdense region, where matter is 20% scarcer than the cosmic average. It's like living in a secluded valley, while assuming the entire world is just as sparsely populated. This raises a startling possibility. What if our galactic address is distorting how we see the universe? For years, astronomers have debated the Hubble tension, the discrepancy between how fast the universe seems to be expanding based on nearby observations versus measurements of the ancient cosmos. One camp argues the expansion rate is around 73 kilometers per second per megaparsec, while another insists it's closer to 67, but if we're sitting in a void, that could solve the puzzle. In less dense regions, gravity's tug is weaker, so galaxies here drift apart slightly faster than they would in a typical part of the universe. Like a marathon runner on a downhill slope, we might be mistaking our local terrain for the entire race course. Critics counter that the KBC void's existence clashes with standard cosmology, which predicts matter should be distributed more evenly. If such a gigantic underdensity is real, it could mean our models are missing something fundamental, perhaps an unknown force tweaking the universe's expansion, or flaws in how we map cosmic structures. Others propose a middle ground. Maybe the void isn't as empty as we think, but filled with dark matter arranged in webs too faint to detect. The implications are profound. If the KBC void is real and skewing our data, it could mean the universe isn't just expanding, it's doing so unevenly, with pockets racing ahead while others lag behind. Picture blowing up a balloon with thinner and thicker patches, some stretching faster than others. That's the unsettling vision some astronomers are grappling with, a cosmos where the rules aren't just written in the stars, but in the voids between them. And here's the twist: what if this void isn't a flaw in our observations, but a clue? Some theorists suggest these vast empties are fingerprints of collisions between universes in the multiverse, leaving behind bruises in space-time. Others wonder if dark energy behaves differently in underdense regions, accelerating expansion in ways we've yet to understand. One thing's certain: the KBC void forces us to confront an uncomfortable truth. We might not just be in the universe, we might be trapped in its blind spot. Imagine flipping a coin 100 times and getting heads every single time. Statistically, it should be impossible, yet that's essentially what astronomers found when they studied the oldest light in the universe. The cosmic microwave background, that faint afterglow of the Big Bang, holds a pattern so bizarre it's been dubbed the axis of evil. And it might append one of cosmology's most cherished principles, the idea that we don't occupy a special place in the universe. Discovered in 2005 by NASA WMAP satellite, this anomaly shows the CMB's temperature fluctuations aren't randomly distributed as expected. Instead, they're weirdly aligned with our solar system's ecliptic plane, the flat disk where Earth and the planets orbit the Sun. It's as if the universe's blueprint were subtly tilted toward us, violating the Copernican principle that insists no observer holds a privileged vantage point. The odds of this happening by chance, less than 1 in 10,000, skeptics argue it's just an illusion, a fluke caused by foreground interference or measurement errors. Perhaps dust in our galaxy subtly warps the CMB signal, or maybe the satellite's calibration wasn't perfect, but even after accounting for these factors, the alignment persists, showing up again in data from the Planck satellite a decade later. If it's not an error, the implications are staggering. It could mean our solar system is cosmically synchronized with the universe's structure in a way that defies all expectations. Some theorists propose radical explanations. One suggests the early universe had a preferred direction, a relic of exotic physics before the Big Bang that imprinted this axis onto space-time. Others wonder if dark energy or dark matter flows along unseen filaments, tugging the CMB into alignment, the wildest idea that we're seeing evidence of a pre-Big Bang universe, a shadow of some earlier cosmic phase poking through the fabric of reality. What makes the axis of evil so unsettling isn't just the data, it's the philosophical vertigo it induces. For centuries, science has dethroned Earth from the center of creation, only to now confront the eerie possibility that our corner of space might not be entirely ordinary. If the universe has a subtle bias toward our solar system, does that mean we're somehow special after all, or is it just a fleeting pattern in the chaos, a cosmic Rorschach test tricking us into seeing meaning where none exists? Every time we map the CMB with sharper precision, the mystery deepens. Maybe future telescopes will reveal this axis as a statistical mirage, or maybe they'll confirm it's real, forcing us to rewrite cosmology's foundational assumptions. Either way, the axis of evil remains one of the universe's most tantalizing riddles, a whisper from the edge of reality that we're only beginning to decipher. Scientists once believed measuring the universe's expansion would be straightforward, like clockwork ticking at a steady pace, but when two of the most trusted methods for calculating this rate began yielding wildly different results, it sparked a crisis in cosmology known as the Hubble Tension. On one side, astronomers using pulsating stars called Cepheids variables pegged the expansion at around 73 kilometers per second per megaparsec. On the other, researchers studying the cosmic microwave background insist it's closer to 67. That 6-kilometer gap might sound small, but in cosmic terms, it's a chasm, one that could force us to rewrite the laws of physics. Let's break down the methods fueling this debate. The Cepheid approach is like measuring the universe's pulse. These stars brighten and dim with a rhythm directly tied to their true luminosity, allowing astronomers to gauge distances to nearby galaxies with remarkable precision. Combine this with observations of how fast those galaxies are receding, and you get the Hubble constant, but the cosmic microwave background method takes a different tack. Instead of looking at the local universe, it analyzes the faint afterglow of the Big Bang itself, using it as a snapshot of the early cosmos. Plug those observations into our best models of how structure forms, and you can extrapolate how fast space should be stretching today. Here's the problem: these two methods should agree. The fact that they don't suggest something fundamental is missing from our understanding. Could there be an unidentified source of interference in the Cepheid measurements? Maybe, but the discrepancy has persisted even as instruments like the Hubble Space Telescope and Gaia satellite refine their data. Alternatively, perhaps our interpretation of the cosmic microwave background is flawed. Yet tweaking the models to reconcile the numbers requires introducing forces or particles we've never detected. One leading hypothesis involves dark energy, the mysterious force accelerating the universe's expansion. What if it's not constant as we assumed, but grows stronger over time? This would mean the cosmos is stretching faster now than in its youth, explaining why local measurements outpace ancient ones. Another wild card is dark matter. If it interacts with itself or ordinary matter in ways we haven't accounted for, that could skew the cosmic ledger. And then there's the nuclear option. Maybe Einstein's theory of gravity itself needs revising on cosmic scales. The stakes couldn't be higher. If the Hubble tension holds, it implies our cosmic map is missing entire continents of physics. Imagine realizing your GPS has been ignoring an invisible hill this whole time, throwing every route off by miles. That's the scale of recalibration astronomers might be facing, a paradigm shift as profound as relativity or quantum mechanics. Until then, the tension remains a tantalizing clue that the universe is still hiding its deepest rules from us, waiting for someone to crack the code. Buried in the faint glow of the cosmic microwave background lies a chilling anomaly, an area of space so cold it defies explanation. Known as the Cold Spot, this mysterious region stretches nearly 200 million light-years across and registers a temperature drop of about 70 microkelvin compared to its surroundings. At first glance that might sound trivial, but in the ultra-precise world of cosmology, it's like finding a frozen patch in a steaming ocean. The most straightforward explanation points to a supervoid, an enormous, underdense region of space where fewer galaxies and less matter mean weaker gravitational effects. As light crosses such a void, it loses energy, shifting to longer, cooler wavelengths, an effect called the integrated Sachs-Wolf effect. But here's the catch: the cold spot is too cold. Simulations show even the largest voids shouldn't produce a temperature dip this extreme. It's like blaming a single missing brick for an entire building's collapse. This mismatch has led to wilder theories. One suggests the cold spot is a scar from a cosmic collision, a bruise left when our universe bumped into another bubble universe in the multiverse. In this scenario, the energy of that impact would have drained away, leaving behind a cold imprint. Others propose it's a defect in spacetime itself, a knot left over from the universe's chaotic birth, like a wrinkle in a crumpled sheet. Then there's the statistical argument: maybe the cold spot is just a fluke, a random fluctuation in the CMB's otherwise smooth tapestry. After all, with trillions of pixels in the cosmic microwave background map, some patch had to be the coldest. But the odds of a dip this severe occurring naturally, less than 2%, that's like rolling a die 100 times and never landing on 6, possible, but vanishingly unlikely. What makes the cold spot so compelling isn't just its temperature, it's the way it exposes gaps in our cosmic models. If it's a void, why is it so much emptier than physics allows? If it's a multiverse collision, where's the other evidence? And if it's just noise, why does it stand out so starkly against the universe's otherwise orderly background? Every new observation deepens the puzzle. Recent surveys found galaxies are sparser in the cold spot's direction, but still not enough to explain its chill. Some researchers now speculate dark energy might be acting differently there, warping space in ways we don't yet understand. Others wonder if quantum effects in the early universe left behind exotic structures now echoing across billions of years. The cold spot remains a frozen enigma, a reminder that even our best maps of the cosmos might be missing whole chapters of its story. Until we crack its secrets, it stands as a silent sentinel at the edge of understanding, a place where the universe whispers its coldest, most cryptic clues. In the vast silence of space, there are whispers so powerful they outshine entire galaxies for just a few milliseconds. These are fast radio bursts, or FRB, some of the universe's most enigmatic signals. Imagine a flash of radio waves packing the energy of 500 suns, lasting no longer than the blink of an eye, and originating from billions of light years away. First detected in 2007, these cosmic firecrackers have puzzled astronomers ever since, but the real twist: some of them repeat. Most FRBs are one-off events, brief, brilliant, and gone forever. But a handful defy expectations, crackling across the cosmos again and again from the same patch of sky. One of the most famous, FRB 121811, has been lighting up telescopes since 2012 with no discernible pattern. It's like a cosmic Morse code operator tapping out messages at random intervals, leaving us scrambling to decode its origin. So what could possibly produce such violent, fleeting bursts? The leading candidate is a magnetar, a type of neutron star with a magnetic field so intense it could strip the data from a credit card halfway across the solar system. When these hypercharged stars undergo starquakes or magnetic eruptions, they might unleash FRBs like cosmic lightning, but there's a problem. Even magnetars struggle to explain the sheer energy of the most distant bursts. Some FRBs appear to come from galaxies so far away, their light has traveled for half the age of the universe. Whatever's producing them must be unimaginably powerful. That's where the wilder theories come in. Could FRBs be the aftermath of colliding black holes, or the death throes of evaporating primordial holes left over from the Big Bang? One provocative idea suggests they're signatures of alien technology, perhaps interstellar probes or energy beams from civilizations harnessing the power of stars. While there's no direct evidence for extraterrestrial origins, the possibility lingers like static in the background, a reminder of how little we know. What makes FRBs so tantalizing isn't just their mystery, it's what they reveal about the cosmos. As these radio waves race across the universe, they pass through clouds of ionized gas, picking up fingerprints of the matter they've traveled through. In a way, FRBs are cosmic probes, helping us map the invisible web of plasma between galaxies. They're also testing Einstein's theory of relativity with every burst. If high-energy and low-energy waves arrive at slightly different times, it could hint at new physics. Yet for all their potential, FRBs remain stubbornly elusive. New telescopes like the Canadian Hydrogen Intensity Mapping Experiment, or CHIME, are detecting dozens of them monthly, but each answer seems to spawn three new questions. Why do some repeat while others vanish? Why do a few seem to cluster in specific regions of space? And what invisible cosmic engines could possibly power these fleeting, universe-spanning flares? One thing's certain, every time an FRB flickers onto our screens, it's a reminder that the universe is far louder and far weirder than we ever imagined. Whether they're the cries of dying stars or the chatter of distant civilizations, these radio whispers from the edge are rewriting the rules of the cosmos 1 millisecond at a time. Rising from the heart of our galaxy like two colossal hourglasses of energy, the Fermi bubbles stretch 50,000 light-years into space, 1/4 the diameter of the Milky Way itself. These towering structures, named after the Fermi Gamma-ray Space Telescope that discovered them in 2010, glow faintly in high-energy gamma rays, invisible to human eyes but unmistakable to our instruments. Picture two vast balloons inflating from the galactic center, filled not with air, but with particles moving at nearly the speed of light. Their sheer scale is humbling. If you could see them from Earth, they'd span half the night sky. So what carved these enormous bubbles out of interstellar space? The prime suspect is Sagittarius, a star, the supermassive black hole lurking at our galaxy's core. Around 6 million years ago, it may have erupted in a cataclysmic feeding frenzy, devouring enormous amounts of matter and belching out jets of high-energy particles that inflated these structures like cosmic bellows. Supporting this theory are ghostly X-ray echoes, hot gas clouds near the bubble's edges that still bear the scars of this ancient violence. But there's a tantalizing alternative: dark matter. Some theories suggest the bubbles could be evidence of dark matter particles colliding and annihilating near the galactic center, where they're thought to cluster most densely. If true, these faint gamma-ray halos might be our first direct glimpse of the universe's most elusive substance at work, yet this explanation comes with its own puzzles. The bubble's symmetrical shape and sharp edges don't quite match what dark matter models predict, leaving researchers debating whether they're seeing astrophysical fireworks or something far more exotic. What makes the Fermi bubbles so intriguing isn't just their origin, it's their timing. 6 million years is a blink in cosmic terms, suggesting our galaxy's quiet middle age might hide a more explosive past. Recent observations reveal filament-like substructures within the bubbles, like scars from multiple outbursts rather than a single event. It's as if Sagittarius, a star, has been periodically clearing its throat across epochs, with each cough leaving its mark on the galactic atmosphere. But the true wonder lies in their persistence. These bubbles have lasted millions of years in the turbulent galactic environment, resisting disruption from stellar winds and magnetic fields. Their longevity hints at forces we're only beginning to understand, perhaps a combination of magnetic containment and ongoing energy injection from the black hole. Every new observation peels back another layer, revealing not just relics of the past, but signposts to the invisible physics shaping our galaxy. For now, the Fermi bubbles remain suspended between two possibilities: a fossil of forgotten violence, or a beacon illuminating dark matter's shadow. Either way, they're proof that even our home galaxy still guards epic mysteries, monuments written in gamma rays, towering over us all. We can see galaxies, stars, and planets, but if you added up all the visible matter in the universe, you'd discover something bizarre. Over half of it is missing. This is the missing baryon problem, one of cosmology's greatest accounting errors. Baryons, the particles that make up ordinary matter like protons and neutrons, should be everywhere. Based on how the universe formed after the Big Bang, scientists calculated how many baryons ought to exist today, yet when they tally everything observable, stars, gas, dust, nearly 50% simply vanishes. So where is it? The leading suspect is something called the warm hot intergalactic medium, or WIM. Picture the universe not as empty space, but as a vast spiderweb of superheated gas filaments connecting galaxies. These threads are so diffuse and faint they're nearly invisible, glowing only in far ultraviolet or X-ray light. The gas here isn't cold enough to form stars, nor dense enough to cast shadows, but collectively, it could hide the missing baryons in plain sight. The challenge detecting WIM is like trying to spot steam rising from a boiling pot miles away. Some astronomers hunt for its fingerprint by studying distant quasars' bright galactic cores, whose light pierces through these cosmic filaments. As that light travels, certain wavelengths get absorbed, revealing the WIM ghostly presence. Others look for subtle distortions in the cosmic microwave background, as if peering through frosted glass. But there's a twist. Even WIM might not account for everything. Some simulations suggest these filaments should be denser than what we observe, meaning part of the missing matter could be hiding in even stranger forms, perhaps as rogue gas clouds flung into intergalactic voids by ancient supernova, or as ultra-diffuse plasma too faint for current telescopes to spot. Then there's the wild card. What if the missing baryons aren't just hiding, but transformed? Under extreme conditions, matter can convert into exotic phases we've yet to discover. Could some baryons have decayed into particles beyond our current physics? It's a long shot, but until every alternative is exhausted, the universe keeps its secrets close. The irony is delicious. We've mapped galaxies billions of light years away, yet can't find half the ordinary matter in our cosmic backyard. Solving this puzzle won't just balance the books, it'll rewrite our understanding of where and what the universe is made of. Shining through billions of light years of cosmic darkness, quasars act as the universe's ultimate lighthouses, their brilliant beams piercing through the void. But when astronomers split their light into spectra, something strange appears. Not a smooth rainbow, but a forest of jagged absorption lines known as the Lyman alpha forest. Each dip in that starlight tells a story, revealing an invisible web of gas clouds strung across the cosmos like dew clinging to a spider's silk. These spectral fingerprints are born when a quasar's light passes through vast clouds of neutral hydrogen, the universe's most abundant element. As photons at specific wavelengths, particularly the Lyman alpha line at 121.6 nanometers, interact with these atoms, they get absorbed, leaving dark gaps in the quasar's otherwise smooth spectrum. The closer the cloud is to us, the more its absorption line shifts toward redder wavelengths due to the universe's expansion. The result, a cascading series of lines across the spectrum, each marking hydrogen at different cosmic distances. It's like reading tree rings, but instead of years, each line encodes millions of light years of space. What makes the Lyman alpha forest revolutionary isn't just its existence, it's what these lines reveal about the universe's skeleton. Simulations predicted that after the Big Bang, matter would clump into a vast cosmic web, with galaxies forming at the intersections of dense filaments. The forest confirms this. Each absorption line traces otherwise invisible strands of gas, mapping the web in 3 dimensions. Some clouds are so diffuse they'd qualify as a vacuum by earthly standards, yet stretched across intergalactic space, they contain more baryonic matter than all stars combined. But the forest has its mysteries. Some regions show far fewer lines than expected, gaps in the cosmic web, where the gas might have been ionized by early galaxies or black holes. Other patches reveal astonishing coherence, with absorption patterns repeating across multiple quasars' spectra, hinting at gas structures spanning hundreds of millions of light years. There's even debate about whether these clouds are truly pristine remnants of the Big Bang, or if they've been subtly polluted by ancient stellar explosions. The most tantalizing possibility, that the Lyman alpha forest holds clues to dark matter's influence. The gas doesn't trace the web perfectly, its distribution is slightly offset, as if invisible hands are rearranging the cosmic scaffolding. By studying these mismatches, astronomers might decode how dark matter shapes the universe's largest structures. For now, every new quasar spectrum adds another twig to this sprawling forest, helping us piece together a map of the universe's hidden anatomy. It's a reminder that even empty space isn't truly empty, just waiting for the right light to reveal its secrets. Among the countless quasars scattered across the cosmos, astronomers have stumbled upon something that defies logic. Their spin axes aren't randomly oriented as expected. Instead, they appear eerily aligned, like compass needles pointing toward some unseen cosmic north. These supermassive black holes, separated by billions of light years, seem to share a preferred direction of rotation, a phenomenon so bizarre it challenges our understanding of how the universe organizes itself on the largest scales. The discovery came when researchers analyzed the polarization of light from nearly 100 quasars. The way these black holes' accretion disks twist light revealed their spin axes, and to everyone's shock, a significant number aligned over distances that should make coordination impossible. Imagine flipping a coin 100 times and getting heads 70 times in a row. That's the level of statistical unlikelihood we're dealing with here. So what invisible hand could be orchestrating this cosmic synchrony? One leading theory points to cosmic strings hypothetical, thread-like defects in spacetime left over from the universe's earliest moments. These ultra-dense filaments, thinner than an atom but stretching across the cosmos, might exert subtle gravitational torques, nudging black holes into alignment like leaves caught in an invisible current. If real, they'd be fossils from a time when the universe was 1 trillion times hotter than the Sun, offering a window into physics far beyond our current models. But cosmic strings aren't the only suspect. Primordial magnetic fields, woven into the fabric of space during the Big Bang, could also be the culprit. These vast ancient fields might have guided the growth of supermassive black holes, forcing their accretion disks to align like iron filings along a magnet's lines. Simulations show that even weak primordial fields, amplified over billions of years by the motions of ionized gas, could leave this kind of imprint on the universe's structure. Then there's the wildest possibility that the alignment isn't physical at all, but a sign we're seeing the universe through a distorted lens. Some theorists suggest an anisotropic expansion, a universe stretching faster in one direction than others, could warp our observations, creating the illusion of coordination where none exists. It's like viewing a field of tilted trees from a hillside and mistaking their angles for a pattern rather than a trick of perspective. What makes this mystery so profound isn't just the alignment itself, it's the timescale. These black holes are so far apart that light from one would take billions of years to reach another, meaning they couldn't have communicated to align their spins. Instead, the pattern must have been locked in place when the universe was a fraction of its current age, preserved like a cosmic fossil. If confirmed, it would mean the universe remembers its infancy in ways we're only beginning to decode. Critics argue the alignment might vanish with more data, a statistical fluke amplified by observational biases, but as telescopes probe deeper into the cosmos, the signal persists, whispering that we might be glimpsing a fundamental asymmetry woven into the universe's very fabric. Whether it's strings, fields, or something even stranger, one thing's clear: the cosmos prefers order in places we least expect it. and that realization could rewrite everything we thought we knew about how the largest structures in existence choose their dance partners. At first glance, the universe should be smooth, matter scattered evenly like flour sifted across a cosmic countertop. That's what the cosmological principle tells us. On the largest scales, everything should look roughly the same in every direction. But then there's the Hercules Corona Borealis Great Wall, a galactic monster so vast it shouldn't exist, stretching an unthinkable 10 billion light-years from end to end. This gargantuan ribbon of galaxies dwarfs even the biggest known structures. If it were real, it would mean the universe is far lumpier and far stranger than we ever imagined. Discovered in 2013 by analyzing gamma-ray bursts, the violent deaths of massive stars, the Great Wall appears as a dense band of galaxies arcing across the northern sky. Picture a sponge where one tiny section is crammed with bubbles, while the rest lies nearly empty. That's what this structure does to our cosmic maps. To put its scale in perspective, if the Milky Way were the size of a grape, the Hercules Corona Borealis Great Wall would be as long as 100 football fields laid end to end. The problem, according to standard cosmology, nothing this colossal should have had time to form after the Big Bang. Gravity simply moves too slowly to clump matter together on such a mind-boggling scale in just 13.8 billion years. It's like expecting a single raindrop to carve the Grand Canyon overnight. Some researchers argue it's not a true structure but a chance alignment, a cosmic mirage created by multiple galaxy clusters overlapping along our line of sight. After all, when you stare far enough into the void, even randomness can start to look like patterns. But here's where it gets weird. The wall's gamma-ray bursts aren't just clustered in space, they are also clustered in time. Many of these stellar explosions happened in the same cosmic epoch, suggesting something about that region of space made it unusually fertile for massive star formation. Was there a primordial density fluctuation, a kink in spacetime left over from the universe's birth that funneled extra matter here? Or could dark energy have sculpted this region differently, accelerating its growth while leaving other patches of the cosmos sparse? Skeptics point to the challenges of mapping structures in 3 dimensions. Distances in astronomy are notoriously tricky to pin down, especially at such extreme ranges. A slight error in measuring how far away these gamma-ray bursts truly are could turn a Great Wall into a scattered handful of unconnected galaxies. Yet even after refining the data, the anomaly refuses to vanish. If anything, newer surveys hint there might be more of these absurdly large structures lurking in the shadows, each one a potential nail in the coffin for the cosmological principle. What makes the Hercules Corona Borealis Great Wall so unsettling isn't just its size, it's the philosophical earthquake it triggers. If the universe isn't uniform, then our entire framework for understanding its evolution might be missing a crucial piece. Perhaps the Big Bang wasn't perfectly smooth, leaving behind wrinkles we're only now detecting, or maybe gravity operates differently on scales so vast we've never been able to test it before. For now, the Great Wall remains perched on the edge between discovery and doubt. Future telescopes, like the European Space Agency's Euclid mission, could settle the debate by mapping billions of galaxies with unprecedented precision. Until then, this cosmic leviathan stands as a ghostly challenge, a whisper that the universe's grandest structures might still be hiding in plain sight. Beneath the cosmic canvas, where galaxies cluster like cities and stars dot the darkness like streetlights, there's a place where the universe simply gives up. The Eridanus supervoid is a staggering emptiness spanning nearly 1 billion light-years, a cosmic ghost town so vast it could swallow our local supercluster whole. But this void isn't just a curiosity, it might hold the key to one of cosmology's most haunting cold cases, the chilling enigma of the CMB Cold Spot. When light travels through a void, it faces a strange dilemma. As space expands within these underdense regions, photons lose energy, stretching their wavelengths and cooling slightly, an effect called the integrated Sachs-Wolf effect. It's like a marathon runner suddenly hitting a downhill slope, slowing their pace as gravity's pull weakens. The Eridanus supervoid is so colossal that light crossing it could lose enough energy to leave a noticeable chill in the cosmic microwave background. That made it the prime suspect for the cold spot's frosty fingerprint, but here's where the mystery deepens. Even with its unimaginable size, the Eridanus supervoid shouldn't be enough. Simulations show that to produce a temperature drop as extreme as the cold spots, you'd need a void far larger and emptier than anything our models predict. It's like finding a freezer in the desert cooler than the surroundings, but not nearly cold enough to explain the iceberg lurking inside. Some researchers argue the void might be layered, with smaller underdensities stacked like Russian nesting dolls, amplifying the cooling effect. Others suggest we're seeing the shadow of something even stranger, a texture defect in spacetime itself, a kink in the universe's fabric left over from the Big Bang. Then there's the problem of timing. The cold spot's location and the supervoid's position don't align perfectly, they're offset just enough to raise eyebrows. Could this mean the void is merely a foreground illusion, a chance overlap that tricks us into seeing a connection where none exists, or is the cold spot's chill the combined work of multiple voids, a cosmic conspiracy of emptiness stretching far beyond our current maps? The implications ripple outward. If voids like Eridanus can cool the CMB this dramatically, it challenges our understanding of how structure forms in the universe. Maybe the cosmos is more uneven than we thought, with gaps and clumps defying the so-called cosmic web we've come to expect. Alternatively, if the supervoid isn't the culprit, then the cold spot's origin becomes even more unsettling, a signpost pointing to physics beyond our standard models, or even evidence of a collision with another universe. For now, the Eridanus supervoid remains both a suspect and a red herring, its true role in the cosmic drama still uncertain. Every new telescope scan peels back another layer, probing whether this billion light-year absence is a key to the universe's secrets, or just another piece of a puzzle we're only beginning to assemble. Either way, it stands as a humbling reminder. Sometimes the most revealing thing about the universe isn't what's there, but what isn't. Every galaxy we observe is fleeing from us, not just moving, but accelerating, as if some invisible hand is stretching the fabric of space itself. This isn't just expansion, it's a cosmic emergency growing faster by the second. The culprit, dark energy, a mysterious force making up 68% of the universe's energy budget, yet we've never seen it, touched it, or even fully defined it. The discovery came in the late 1990s, when two teams studying distant supernova made an unsettling observation. These exploding stars, used as cosmic mile markers, were dimmer than expected, meaning they were farther away than classical expansion models predicted. The universe wasn't just coasting apart, it was pressing the gas pedal. The implication sent shockwaves through physics. Either Einstein's theory of gravity was incomplete, or some unknown energy permeated the void, pushing galaxies apart like an anti-gravity force. One leading explanation frames dark energy as the cosmological constant, a term Einstein once added and later discarded to his equations, representing a uniform energy density woven into space itself. If accurate, it means empty space isn't truly empty but crackles with latent energy that grows stronger as the universe expands. The catch, quantum physics, predicts this energy should be 120 orders of magnitude stronger than observed. That's like calculating a candle's heat and getting temperatures hotter than the Big Bang instead. Enter quintessence, a more dynamic alternative. Unlike the static cosmological constant, quintessence proposes dark energy as a fluid-like field that varies across space and time. Imagine the universe as an ocean, with currents of dark energy flowing and shifting, sometimes pulling galaxies apart, other times letting gravity take the wheel. Some models even suggest it could eventually reverse, collapsing the cosmos in a big crunch, but despite decades of searching, no telescope has detected quintessence's fingerprint. Then there's the nuclear option. Maybe Einstein's theory of gravity itself breaks down on cosmic scales. Modified Newtonian dynamics, or MIND, suggests tweaking gravity's equations to eliminate the need for dark energy entirely. Yet even MIND struggles to explain all the data, like the intricate patterns in the cosmic microwave background, which align eerily well with dark energy models. What makes this enigma so profound isn't just the unanswered questions, it's the stakes. If dark energy continues unchecked, it could eventually tear apart everything, from galaxies to atoms, in a big rip. Alternatively, if it fades, gravity might reverse the expansion, collapsing the universe into a singularity, or perhaps it's just one chapter in a cycle of cosmic births and deaths we've yet to comprehend. For now, dark energy remains the universe's most dominant, yet elusive, tenant and invisible architect reshaping reality while we scramble to decode its blueprints. Every new observation, from galaxy surveys to gravitational wave detectors, brings us closer to understanding whether we're witnessing the universe's grand finale or just the first act. Picture the universe in its final moments, not with a bang but with a scream. The Big Rip is dark energy's ultimate victory, a scenario so violent it would shred reality itself. Here's how it could happen. If dark energy's repulsive force grows stronger over time, it wouldn't just push galaxies apart, it would overpower every force holding the cosmos together. First, galaxy clusters would tear free from one another, vanishing into isolated darkness. Then, individual galaxies would unravel, stars flung into the void like sparks from a dying fire. Next, solar systems would disintegrate, planets ripped from their orbits. Finally, in the last microseconds, even atoms would be torn apart, their nuclei shattered by the unstoppable expansion of space itself. The timeline, it could be surprisingly swift. Calculations suggest if dark energy's strength crosses a critical threshold, the Big Rip might occur just 22 billion years from now, a blink in cosmic terms. For perspective, that's only about 10 times the universe's current age. The countdown could start with subtle clues. Galaxies at the edge of our observable horizon would wink out first, their light stretch beyond detection as space's expansion outpaces the speed of light. Then nearer structures would vanish, like a blackout rolling across the cosmos. But how would we know if this nightmare scenario is truly our future? Astronomers hunt for telltale signs in the universe's expansion rate. If dark energy is truly accelerating, not just constant but growing stronger, we'd see distant supernova dimming faster than expected, and the cosmic microwave background showing asymmetrical stretching. There's even a proposed doomsday test, measuring whether galaxy clusters are being pulled apart faster than gravity can hold them, like sandcastles facing an incoming tide. The terrifying beauty of the Big Rip lies in its inevitability. If dark energy behaves this way, no force could stop it, not gravity, not nuclear bonds, not even the fabric of quantum fields. Yet it's also a reminder of how fragile our cosmic order really is, balanced on a knife's edge of forces we're only beginning to understand. Whether this fate awaits us or not, the search for answers is rewriting what we know about time, energy, and the very nature of existence. Black holes are cosmic riddles wrapped in event horizons, but perhaps their greatest puzzle isn't what they destroy, but what they supposedly erase. This is the black hole information paradox, a crisis at the heart of physics that Stephen Hawking exposed in the 1970s. According to quantum mechanics, information, the fundamental blueprint of every particle's properties, can never truly vanish. Yet Hawking showed black holes radiate energy, slowly evaporating over eons until they disappear. Taking all that swallowed information with him, it's as if you burned a library and the smoke contained not the words of every book, but pure, meaningless heat. Enter the holographic principle, one of the most mind-bending solutions proposed. Imagine the event horizon isn't just a point of no return, but a frenetic, two-dimensional surface encoding all the information of what falls inside, like a cosmic DVD where three-dimensional reality gets flattened into a shimmering hologram. This idea suggests black holes don't destroy information, they scramble and store it on their surfaces, releasing it back into the universe through Hawking radiation's subtlest fluctuations. Picture throwing a clock into a black hole. Over millennia, its gears and springs would dissolve, but the information about those parts lingers, etched onto the horizon's surface in quantum bits so fine we can't yet decode them. Then there's the firewall hypothesis, an even more radical fix. If information can't be lost, maybe it never makes it past the event horizon at all. Instead, an inferno of high-energy particles might lurk just inside, instantly vaporizing anything that crosses. It's like realizing the library's doors aren't an entrance, but a shredder, preserving information by never letting it reach the interior. Critics argue this violates Einstein's equivalence principle, which states free fall into a black hole should feel uneventful, no flames, no drama. Yet supporters counter that quantum mechanics might demand such violent revisions to gravity's rules. Recent breakthroughs add dizzying twists. In 2019, physicists calculated that quantum hair, subtle gravitational imprints left on black holes by what they consume, could preserve information without breaking known physics. Others explore wormholes linking black holes to distant points in spacetime, where information might secretly escape. Meanwhile, lab experiments with analog black holes, made of supercooled atoms or light pulses, test these theories in miniature, hunting for clues in controlled quantum chaos. The paradox remains unsolved, but the stakes couldn't be higher. If information can vanish, it undermines quantum theory's bedrock. If it can't, we might need a grander framework merging gravity and quantum mechanics, a theory of everything. Every twist in this cosmic detective story reveals how little we grasp about reality's deepest laws, and how black holes, those darkest of enigmas, might be the key to illuminating them. On a quiet summer night in 1877, a radio telescope in Ohio picked up something extraordinary, a burst of noise so powerful it made an astronomer scrawl, "Wow." In the margins of the data printout, for 72 seconds the signal blared at a frequency of 1420 MHz, the exact range where cosmic background noise is lowest and interstellar messages would logically stand out. It came from the direction of Sagittarius, near the center of the galaxy, and then vanished. No repetition, no trace, just those tantalizing 72 seconds that have fueled debates for decades. What made the WOW signal so electrifying was its precision. It wasn't the crackle of a distant quasar or the static of a passing satellite. It was narrowband, meaning it occupied an extremely specific sliver of the radio spectrum, the kind of signature you'd expect from a deliberate transmission, not natural cosmic noise. Even stranger, it matched predictions for how an alien civilization might broadcast its presence, leveraging the hydrogen line frequency, a universal marker any advanced species would recognize. For a brief moment it seemed like we might not be alone, yet the mystery only deepened when follow-up searches turned up nothing. The Very Large Array, the SETI Institute's Allen Telescope Array, all listened intently for a repeat that never came. Some argue the signal was Earth-based interference bouncing off space debris, though no military or civilian transmissions matched its profile. Others pointed to a passing comet, like 266P/Christensen, suggesting hydrogen clouds in their tails might emit similar frequencies. But when astronomers revisited the data, the timing and location didn't quite align. The comet theory, while creative, left more questions than answers. Then there's the unsettling possibility that we simply missed the point. What if the WOW signal wasn't meant to be a continuous broadcast, but a fleeting beacon, a cosmic hello, sweeping past Earth like a lighthouse beam? Or worse, what if it was repeating, but on a time scale we haven't been patient enough to catch? Modern SETI projects now scan for sporadic signals, but the original equipment in 1877 wasn't designed for such unpredictability. The debate rages on, balancing between hope and skepticism. Recent machine learning algorithms have sifted through terabytes of radio data, hunting for echoes of that iconic burst. Some researchers even propose it could have been a one-time astrophysical event we don't yet understand, a natural phenomenon masquerading as artificial. But the allure of the WOW signal endures because it represents the ultimate cosmic tease, a whisper from the void that refuses to be explained, leaving us forever wondering if we were seconds away from first contact, or just victims of the universe's cruelest coincidence. In the vast emptiness between planets where sunlight fades to a dim glow, two spacecraft began drifting off course, not by much, but enough to baffle scientists for decades. The Pioneer anomaly refers to the tiny, unexplained deceleration detected in NASA Pioneer 10 and 11 probes as they journeyed toward the edge of our solar system. By the late 1980s, tracking data revealed both probes were slowing ever so slightly, as if an invisible hand were tugging them backward. The discrepancy was minuscule, about 300,000 times weaker than Earth's gravity, but in the precision-driven world of astrophysics, even the faintest anomaly can rewrite textbooks. At first, researchers suspected mundane explanations, perhaps uneven thermal radiation from the probe's plutonium power sources was pushing back like a faint cosmic breeze. After all, heat emitted from one side more than the other could create just enough recoil to account for the drift. Teams spent years modeling every nut, bolt, and watt of energy on the spacecraft, but the numbers never quite added up. The thermal theory explains some of the anomaly, but not all, leaving a tantalizing gap in our understanding. That's when the speculation turned cosmic. Could there be unseen masses lurking in the Kuiper belt, their gravity gently braking the Pioneer's escape? Or might dark matter, the invisible scaffolding of the universe, be clustered near our solar system, subtly altering the probe's trajectories? Some theorists ventured even further, proposing modifications to Newton's laws of motion at extreme distances, suggesting gravity itself might behave differently in the icy reaches of interstellar space. The most electrifying possibility, that the Pioneers brushed against an unknown gravitational phenomenon, a shadow of physics we've yet to map. Imagine the edge of the solar system not as a clean boundary, but as a zone where familiar rules bend. Just as ocean currents shift near a coastline, perhaps space-time warps imperceptibly where the sun's influence wanes, creating subtle ripples that tug on passing objects. Then in 2012, a painstaking analysis cracked the case, or so it seemed. By reconstructing decades-old thermal models with modern computing power, researchers concluded that heat radiating asymmetrically from the probe's instruments could, in fact, explain the anomaly. Case closed, not quite. Skeptics noted lingering inconsistencies, especially with Pioneer 11's data, and even if thermal radiation was the primary culprit, the episode exposed how little we truly understand about the complex interplay of forces in deep space. The Pioneer's mystery endures as a cautionary tale, a reminder that even our most trusted models of the universe might hide blind spots. Today, as newer probes like Voyager and New Horizons venture farther than ever, scientists watch closely for any sign of similar anomalies. Because sometimes the universe's quietest whispers hold the loudest secrets, in October 2017, astronomers spotted something streaking through our solar system that didn't belong, a mysterious visitor from interstellar space, tumbling end over end at nearly 200,000 miles per hour. They named it Oumuamua, Hawaiian for scout, and at first glance it seemed like just another comet, but the closer scientists looked, the stranger it became. For starters, its shape defied all expectations. A bizarre, elongated slab roughly 10 times longer than it was wide, unlike any asteroid or comet we'd ever seen. And then there was the acceleration. Instead of slowing predictably as it moved away from the sun, Oumuamua sped up, as if something were pushing it. The most unsettling part, no visible outgassing, the telltale plumes of gas and dust that typically explain a comet's speed boosts. Without this cosmic exhaust, Oumuamua's acceleration made no sense under conventional physics. Some researchers scrambled for natural explanations. Maybe it was a hydrogen iceberg, a chunk of frozen hydrogen vaporizing silently in sunlight, providing invisible thrust. Others suggested it could be a fragment ripped from a Pluto-like world, its nitrogen ice sublimating undetected, but each theory had holes. Hydrogen ice should evaporate rapidly in interstellar space, and nitrogen would have left traces we could have spotted. Then came the electrifying, controversial alternative: could Oumuamua be artificial? Harvard astronomer Avi Loeb famously floated the idea that it might be a light sail, a thin, reflective structure propelled by solar radiation, perhaps even debris from an alien civilization. The shape fit, the acceleration fit, even its brightness variations, flaring periodically as it tumbled, matched what you'd expect from a flat, reflective surface catching sunlight. Critics dismissed this as sensationalism, arguing extraordinary claims require extraordinary evidence, but Loeb countered, if we're searching for extraterrestrial technology, shouldn't we consider the most exotic possibilities when the data resists mundane explanations? The debate rages on, fueled by Oumuamua's frustrating elusiveness. By the time we noticed it, the object was already racing out of sight, leaving behind a trail of questions. Future telescopes like the Vera Rubin Observatory might spot more of these interstellar interlopers, helping us determine whether Oumuamua was a cosmic oddball or the first hint of something far more profound. Until then, it remains a Rorschach test for how we view the universe: a rock, a relic, or perhaps a message in a bottle we're not yet equipped to read. Every galaxy we've ever studied dances to the same cosmic rhythm, swirling stars held together by the gravitational grip of unseen dark matter. That is, until astronomers stumbled upon UC 1052 DF2, a ghostly galaxy that plays by its own rules. This cosmic rebel, floating 65 million light-years away in the constellation Cetus, spins too slowly, weighs too little, and most shockingly appears to have no dark matter at all. It's like finding a car speeding down the highway with no engine inside. The discovery sent shockwaves through astrophysics, because dark matter isn't just an ingredient in galaxies, it's the scaffolding of the universe. Models suggest galaxies form when dark matter clumps together, creating gravitational wells that pull in gas and stars. Without it, NGC 1052 DF2 shouldn't exist, or at least shouldn't look so. Normal its stars drift lazily, their motions perfectly explained by the visible matter alone. No hidden mass, no mysterious tug, just an eerie, almost too orderly cosmic island. But how could a galaxy lose its dark matter, or avoid having it in the first place? One leading theory involves tidal stripping, the idea that a nearby galaxy's gravity might have ripped away NGC 1052 DF2's dark matter like a thief in the night. Picture two dancers whirling past each other. The larger partner could yank away the smaller one's invisible cloak without tearing apart its stars. Supporting this, astronomers found the galaxy lives near a massive elliptical galaxy, NGC 1052, which could have bulleted over billions of years. Then there's the more radical possibility: dark matter isn't as universal as we thought. Maybe certain rare regions of the universe forged galaxies through different processes, assembling stars without the usual dark matter crutch. Some theorists even speculate NGC 1052 DF2 could be a failed galaxy, born from gas too turbulent to attract dark matter in the first place. Critics, though, argue the anomaly might lie in our measurements. Determining a galaxy's dark matter content relies on calculating star velocities, which can be tricky for ultra-diffuse galaxies like this one, where stars are sparsely scattered. A handful of rogue stars moving unusually fast could skew the data, making it seem like dark matter is missing when it's actually hiding in plain sight. Follow-up observations added fuel to the fire. another dark matter-deficient galaxy, NGC 1052 DF4, was found nearby, suggesting this might be a family of cosmic oddballs. The implications are profound. If galaxies can exist without dark matter, it challenges our entire understanding of how structures form in the universe. On the other hand, if tidal stripping is the culprit, it reveals how dynamic and violent galactic neighborhoods can be, reshaping their members over eons. Either way, NGC 1052 DF2 forces us to confront an uncomfortable truth. The universe might have more than one recipe for building a galaxy, and we've only just begun to read the cookbook. For now, this enigmatic galaxy remains a cosmic Rosetta Stone, a cryptic clue that could either upend dark matter theory or teach us how resilient galaxies can be when stripped of their shadowy skeletons. Every new telescope trained on it brings us closer to decoding whether it's a rebel without a cause or a pawn in a much larger galactic game. When the James Webb Space Telescope peered deeper into the cosmos than ever before, it didn't just find ancient galaxies, it found galaxies that shouldn't exist. These cosmic relics, spotted just 300 million years after the Big Bang, are far bigger, brighter, and more structured than our models predicted. They're like stumbling upon a skyscraper in the middle of the Stone Age, defying everything we thought we knew about how the universe built its first cities of stars. The shock comes from their sheer maturity. These early galaxies are packed with old stars, heavy elements, and well-defined shapes features that should take billions of years to develop, not a few hundred million. It's as if someone hit fast forward on cosmic evolution, leaving astronomers scrambling to explain how such complexity emerged so soon after the universe's birth. Some galaxies even appear to be fully formed spirals, a structure so delicate it shouldn't survive the violent mergers and chaotic conditions of the early cosmos. One radical explanation rewinds the cosmic clock entirely. What if the Big Bang happened earlier than we think? Pushing the universe's age back by a few hundred million years would give these galaxies more time to grow. But this tweak would ripple through all of cosmology, forcing revisions to the cosmic microwave background's timeline and potentially clashing with other well-tested predictions. Others suggest dark matter behaved differently in the early universe, clumping faster and seeding galaxies sooner than modern simulations allow. Imagine dark matter not as a sluggish scaffold, but as an eager architect, racing ahead of schedule. Then there's the nuclear option. Maybe our understanding of galaxy formation is missing a fundamental piece. Perhaps early stars formed far more efficiently, converting gas into suns at breakneck speed, or supermassive black holes grew unnaturally fast, heating and shaping their surroundings like cosmic blacksmiths. Some theorists even float the idea of dark stars, hypothetical, fuel-rich behemoths powered by dark matter annihilation, which could have lit up the early universe with unimaginable brightness. Critics caution against overinterpreting the data. Could these galaxies simply be outliers, the equivalent of finding a few precocious children in a kindergarten class, or might distortions from gravitational lensing, the warping of light by intervening matter, be making them appear artificially large and bright? Follow-up observations are ongoing, but with each new JWST deep field image, the anomaly grows harder to dismiss. What makes this mystery so electrifying isn't just the galaxies themselves, it's what they represent. If the early universe could forge mature galaxies against all odds, what other surprises are lurking in those first flickers of light? Every unexpected spiral, every too heavy element, whispers that our cosmic story might need more than a few footnotes. It might need a whole new chapter, stretching across billions of light years like the veins of a colossal cosmic leaf. The universe's large-scale structure reveals an astonishing pattern, not random scatterings of galaxies, but a delicate web of interconnected filaments. This is the cosmic web, and its origins trace back to the universe's first whispers, when quantum fluctuations smaller than atoms ballooned into the scaffolding for everything we see today. Picture the infant cosmos as a bubbling quantum foam, where tiny ripples in spacetime smaller than a proton were stretched exponentially during inflation, frozen into the fabric of reality like fingerprints on wet clay. These microscopic wrinkles became the seeds for all structure, the hidden blueprint for the grand design we now observe. Dark matter plays the silent architect in this story. Invisible yet dominant, it formed vast halos around these early density fluctuations, creating gravitational wells that funneled ordinary matter, hydrogen and helium into sprawling tendrils. Simulations show this dance in stunning detail. Dark matter's tendrils snake through the void, intersecting at nodes where galaxies cluster like pearls on a string. Without dark matter's gravitational grip, the cosmic web would never have cohered. Galaxies would drift apart, unmoored in an aimless sea of gas. It's as if the universe wove itself together using threads we can't even see, stitching galaxies into place with dark matter's unseen hand. The most striking simulations come from projects like Illustris and TNG, which model billions of particles interacting over cosmic time. Watch one unfold, and you'll see the web emerge, a shimmering, fractal network where gas heats and cools, stars ignite, and black holes flicker to life at the intersections. These virtual universes reveal how delicate the balance truly is. Tweak the initial conditions slightly, and the web might dissolve into chaos or clump into unrecognizable knots. Yet against all odds, our universe found the perfect recipe, spinning quantum noise into silk, but mysteries linger at every scale. Why do some filaments stretch for hundreds of millions of light years, while others fray into sparse strands? How do supermassive black holes, seated at the web's nodes, regulate galaxy growth like cosmic gatekeepers, and what role did dark energy play, subtly accelerating the web's expansion even as gravity tried to pull it tight? Each question peels back another layer, revealing how deeply interconnected the cosmos truly is, from quantum froth to galaxy clusters, all bound by the same invisible threads. The cosmic web isn't just a relic of the past. Even now it pulses with activity. Galaxies slide along filaments like beads on a wire, drawn toward colossal intersections like the Laniakea supercluster, our galactic neighborhood's gravitational hub. Gas streams between these tendrils, fueling star birth in some regions and starving others, shaping the fate of galaxies we'll never see. It's a living, breathing structure, one whose origins still echo in the night sky, written in the silent language of dark matter and quantum chance. What if our universe is just one bubble in an endless cosmic foam? This is the multiverse hypothesis, the idea that reality extends far beyond what we can observe, with countless universes popping into existence like bubbles in a boiling pot. The theory emerges from inflationary cosmology, which suggests that in the instant after the Big Bang, space expanded faster than light, stretching quantum fluctuations into vast cosmic structures. But here's the twist: if inflation never truly stopped, it could still be happening right now in distant regions of space, birthing new universes with every fraction of a second. These bubble universes aren't just far away, they're fundamentally separate, each enclosed in its own pocket of spacetime with its own unique physics. Think of it like a cosmic lava lamp. Where two bubbles collide, you might see scars in the cosmic microwave background, but most drift apart forever, never interacting. This is the Level 2 multiverse, where the very rules of reality, the strength of gravity, the mass of electrons, even the number of dimensions could vary from bubble to bubble. Some might be lifeless voids, others might flicker in and out of existence in nanoseconds, and a rare few could harbor conditions just right for life like ours. But there's a humbler version of the multiverse already hiding in plain sight, the Level 1 multiverse. If space is infinite, as measurements of the cosmic microwave background suggest, then somewhere beyond our cosmic horizon, there must be regions where every possible configuration of matter repeats. Imagine a universe-sized deck of cards, Shuffle it enough times and eventually you'll deal the same hand twice. Far enough away, there could be an identical Earth where every choice you didn't make plays out, every historical event unfolds slightly differently, or where you never existed at all. The difference between these levels isn't just scale, it's physics. Level 1 relies on known cosmology, just extended to infinity. Level 2 demands new theories, like string theory's landscape of possible universes, where extra dimensions curl up in trillions of ways, each creating a unique set of physical laws. Some physicists argue this isn't science at all, since we can't observe other universes. Others counter that the multiverse explains fine-tuning, why our universe's constants seem perfectly calibrated for life. If every possibility exists somewhere, it's no surprise we find ourselves in a bubble where conditions allow us to ask the question. Critics call it a cop-out, a way to avoid deeper explanations. Supporters see it as cosmic humility, a reminder that our universe might not be the main event, just a single page in an infinite library. Either way, the multiverse forces us to confront the limits of knowledge. If there are realms where time runs backward or gravity repels, how could we ever prove it? And if we're alone in this bubble, does that make it more precious or less? The answer might lie beyond the edge of existence itself. Here's a nightmare to keep you up at night. What if you're not a person watching this video, but a momentary glitch in the void, a flicker of self-awareness conjured from pure randomness? This is the Boltzmann brain paradox, a thought experiment so unsettling it forces us to question the nature of reality itself. Imagine the universe given infinite time. Eventually, even the most improbable events become inevitable, including the spontaneous formation of a fully conscious brain, complete with false memories of a past that never existed, floating alone in the darkness. The paradox traces back to 19th century physicist Ludwig Boltzmann, who realized entropy, the universe's tendency toward disorder, doesn't rule out rare, fleeting moments of order. In a sufficiently vast or eternal cosmos, random particle interactions could, by sheer chance, assemble a functioning mind. Statistically, these disembodied brains should outnumber real, evolved observers like us by an unimaginable margin. So why do we find ourselves embedded in a coherent universe with 14 billion years of history, rather than as cosmic phantoms hallucinating existence into being? One escape route invokes the arrow of time. Our universe's low entropy beginnings, the Big Bang's improbable orderliness, might act as a cosmic safeguard, making Boltzmann brains vanishingly rare compared to legitimate observers. But this just shifts the puzzle. Why did the universe start with such precise conditions to begin with? Some cosmologists argue eternal inflation, the multiverse's endless bubble spawning, could amplify the problem, creating infinite regions where Boltzmann brains dominate. If true, the statistical weight of these apparitions might render our own experiences suspect. Others attack the paradox's foundations. Quantum mechanics suggests true randomness might not allow for the precise particle arrangements needed to sustain even an instant of coherent thought. Or perhaps consciousness isn't something that can emerge from chaos at all. It might require the intricate scaffolding of a biological brain, or even a soul, defying purely materialist explanations. The darkest implication: if Boltzmann brains are possible, we can't trust any observation, memory, or scientific conclusion. The laws of physics you just read about might be a figment of your momentary existence. The universe you think you're studying could dissolve in the next instant, taking you with it, its solipsism cranked to cosmic scales, a horror story written in the language of thermodynamics. Yet the paradox isn't just a philosophical toy. It pressures cosmologists to refine theories that would otherwise permit such absurdities. Any model of the universe that predicts Boltzmann brains as likely outcomes, like certain interpretations of quantum fluctuations in a vacuum, faces a brutal reckoning. Reality, it seems, has a preference for grounding minds in something sturdier than quantum noise, so the next time you feel certain of anything, the sun rising, your own name, even the screen before you remember, the Boltzmann brain warns that certainty might be the most fleeting illusion of all. Unless, of course, this sentence is just part of your brief, flickering delusion. We take for granted that space stretches on forever in every direction, but what if the universe isn't infinite at all? What if it's folded in on itself like an origami puzzle, its edges stitched together in ways we can't see? This is the enigma of cosmic topology, the study of the universe's shape on the grandest scales. Forget flat sheets or simple spheres. Some theories suggest space might twist into a donut like torus, a Möbius strip writ large, or even a kaleidoscopic hall of mirrors where light loops back on itself. The implications would rewrite physics, philosophy, and our very place in reality. For centuries, astronomers assumed the cosmos was either an infinite plane or a vast, closed sphere, two tidy options with clear geometries. But when scientists measured the cosmic microwave background with unprecedented precision, they found something odd. Large-scale temperature fluctuations seemed missing. The patterns were there, just fainter than models predicted, as if space itself were blurring the signal. One explanation: a multiply-connected universe, where space isn't simply open or closed but woven. Picture a video game where exiting the right edge teleports you to the left, except on a cosmic scale, where a galaxy vanishing over one horizon might reappear on the opposite side, ghostly and repeating. The most tantalizing candidate is the 3 torus, a donut shape extended into higher dimensions. In this model, traveling far enough in one direction would bring you back where you started, like an ant crawling around a giant, unseen loop. Support comes from strange statistical quirks in the CMB, including anomalous correlations between distant points that shouldn't know about each other in a standard infinite universe. It's as if the cosmos were whispering hints of its hidden seams. Then there's the Poincaré dodecahedral space, a mind-bending structure where the universe is a 12-sided die folded into a hyperdimensional balloon. Light traveling through this shape would create mirrored images of the same galaxies, explaining why some deep-field telescope shots show eerily similar galaxy clusters in seemingly unrelated patches of sky. Critics argue these patterns could just be chance alignments, but the math holds unsettling elegance. Proving any of this, though, is like trying to sense the curve of Earth while standing in a meadow. To uncover the universe's true topology, astronomers hunt for matching circles in the CMB, identical patterns of hot and cold spots that would appear if space loops around. So far, none have been confirmed, but the search continues with increasingly sophisticated algorithms. Another clue might lie in gravitational waves, which could carry imprints of space's underlying structure as they ripple through the cosmos. The stakes are cosmic. If the universe is finite yet unbounded, it would mean everything we see, every galaxy, every quasar, every distant supernova is just one tile in a grand, repeating mosaic. And if space is multiply-connected, even the edge of the observable universe might be an illusion, a trick of perspective hiding the fact that we've been staring into a mirror all along. For now, the universe guards its ultimate shape like a sphinx's riddle, but every new map of the microwave background, every simulation of exotic geometries, brings us closer to answering one of existence's oldest questions: are we floating in an endless sea, or sailing the surface of a vast, invisible labyrinth? The answer might rewrite not just the cosmos, but our place within it. The Big Bang marks the beginning of everything we know, but what if it wasn't the true beginning at all? Imagine the universe as a cosmic heartbeat, expanding and contracting in an endless cycle, where each Big Bang is just the latest in an infinite series of rebirths. This is the cyclic universe model, a radical reimagining of time itself that throws open the door to what was before our cosmos came into being. In this vision, the Big Bang wasn't a singular eruption from nothingness, but a violent turning point where a previous universe collapsed and rebounded. Picture a black hole forming in some distant, dying reality, its crushing singularity birthing a new space-time bubble, our own universe. The equations of string theory and loop quantum gravity suggest such a scenario isn't just poetic speculation, the math allows for it. What we perceive as time zero point might be a bridge between cosmic epochs, a phase transition as natural as ice melting into water. Even stranger is conformal cosmology, which proposes that time loses all meaning as you rewind toward the Big Bang. In this framework, the before isn't a void or a prior universe, but a state so symmetrical that past and future blur into irrelevance, scale shrinks to zero, temperatures soar to infinity, and yet, mathematically, the universe remains indistinguishable from its mirror image. It's like trying to find the start of a circle. The question itself becomes meaningless. Then there's the quantum gravity era, a realm where space-time itself shatters into foam-like turbulence. Here, traditional physics breaks down and time becomes a fractured concept. Some theories suggest that in this primordial chaos, tiny baby universes bud off from the larger fabric, each with its own laws of physics. Our universe might just be one leaf on an infinite tree, sprouting from a branch we can never see. Contrast this with the classical view, a singularity where all matter, energy, and even time itself were crushed into a mathematical point. No before, no space, no questions, just an absolute beginning. But this narrative feels increasingly incomplete, like reading a novel starting from chapter 2. The cosmic microwave background's uniformity hints at something smoothing the universe's wrinkles before the bang, a process called inflation, but what triggered that? The most unsettling possibility, that time itself is an illusion, a byproduct of our limited perspective. Just as a two-dimensional being couldn't comprehend depth, we might be incapable of perceiving the true structure of reality's origins. Whether cyclical, conformal, or quantum, one thing's clear: the phrase "before the Big Bang" might soon need redefining, if it means anything at all. What if everything you see, touch, and experience, the stars, the laws of physics, even your own thoughts, is nothing more than lines of code in an unfathomably advanced simulation? This is the simulation argument, a hypothesis that's evolved from sci-fi trope to serious scientific debate. At its core lies a chillingly simple premise: if any civilization could achieve the computing power to simulate conscious beings, and if they had even a slight desire to do so, the number of simulated minds would vastly outnumber biological ones. Statistically speaking, the odds that we're the original base reality species shrink to near zero. The idea gained traction when philosopher Nick Bostrom formalized it in 2003, breaking it into three bleak possibilities: either civilizations always go extinct before reaching simulation capability, they lose interest in creating ancestor simulations, or we're almost certainly living in one. The first two scenarios seem unlikely given humanity's own trajectory, so by elimination, the third option looms large. But beyond philosophy, physicists have begun hunting for empirical evidence. If our universe is a simulation, there might be glitches in the matrix, artifacts of finite computational resources, one potential smoking gun, Planck-scale pixelation. Just as a digital image breaks down into discrete pixels when zoomed in far enough, spacetime itself might reveal a granular structure at the tiniest measurable scale, the Planck length. Some quantum gravity models already suggest space isn't perfectly smooth, but fragmented into fundamental units. Experiments aiming to detect this graininess involve ultra-high-energy cosmic rays. These particles, accelerated to near light speed by distant black holes or supernova, should lose energy differently if space is pixelated, leaving telltale gaps in their observed spectra. So far, results are inconclusive, but the hunt continues with particle colliders and quantum sensors probing ever smaller scales. Another test probes the universe's rendering limits. In a simulation, complex systems like human consciousness might only be fully computed when observed. a cosmic version of video game graphics that load details as players approach. Physicists have proposed double-slit experiments with increasingly large molecules to see if quantum superposition, the ability of particles to exist in multiple states until measured, breaks down for objects massive enough to strain hypothetical processing power. If reality starts behaving like an overloaded computer, skipping computations to save resources, it could hint at underlying code, but the simulation hypothesis isn't without critics. Some argue it's unfalsifiable, an untestable claim masquerading as science. Others point out that simulating every quantum particle in a universe would require more energy than exists in that universe, making the idea physically absurd. Unless, of course, the simulators found shortcuts, approximating reality the way video games fake sprawling landscapes with clever algorithms. Then there's the existential twist: if we're simulations, could our creators be simulations too, nested in an infinite regression of fake universes? Or worse, what if they shut the experiment down? The simulation argument forces us to confront not just the nature of reality, but the fragility of our place within it. Whether glitching pixels or cosmic coincidences, every anomaly we uncover might be a breadcrumb trail, one that leads either to humanity's greatest revelation or its most humbling dead end. The universe is unimaginably vast, teeming with billions of galaxies, each containing billions of stars. So where is everyone? This is the Fermi paradox, the haunting contradiction between the high probability of alien civilizations and our total lack of evidence for them. But as we peer deeper into the cosmos, especially toward its most mysterious edges, a radical possibility emerges: maybe we're not listening the right way. Advanced civilizations might have transcended the need for radio signals or Dyson spheres, tapping into phenomena we can't even conceive of yet. Consider the Great Attractor or dark float, those colossal, unexplained gravitational forces tugging at galaxies. Could they be artifacts of engineering on a scale we can't fathom? A Type 3 civilization, harnessing the energy of entire galaxy clusters, might manipulate spacetime itself, bending gravity to their will like a sculptor shaping clay. Their technology wouldn't just be advanced, it would be fundamentally unrecognizable to us, blending seamlessly into the fabric of the universe. Instead of searching for radio transmissions, we might need to look for distortions in cosmic expansion, anomalies in dark matter distribution, or even intentional patterns woven into the cosmic microwave background. Then there's the eerie silence of the Boötes void and other cosmic deserts. If life thrives in resource-rich regions, why wouldn't a hyper-advanced species expand into these empty frontiers, using them as laboratories or sanctuaries? The absence of galaxies could be deceptive. What if the void is actually a hub of activity, but operating in dimensions or energy states we can't perceive? Quantum communication, dark matter networks, or even consciousness existing as pure information could render their presence invisible to our crude instruments. Even time itself might hide the answer. The universe is 13.8 billion years old, plenty of time for civilizations to rise, evolve, and vanish long before Earth formed. They might have left behind relics encoded in the structure of spacetime, like ghostly fingerprints on the edge of existence. The Lyman alpha forest, those delicate absorption lines in quasar light, could carry messages compressed into hydrogen's quantum states, waiting for us to develop the right decryption key. The most unsettling thought: if intelligence inevitably leads to harnessing dark energy or manipulating entropy, perhaps the silence isn't accidental. Advanced civilizations might transcend physical form, uploading into synthetic realities or merging with the universe's underlying code. In that case, the cosmos isn't empty, it's full of beings who have become one with the void, leaving no trace we'd recognize. The Fermi paradox forces us to confront not just the absence of aliens, but the limits of our own imagination. The answers may not lie in the stars, but in the gaps between them, where reality bends and the rules as we know them no longer apply. Every star will burn out, every black hole will evaporate, even the fabric of spacetime itself might not be eternal. So how does the universe end? The answer lies in a cosmic tug-of-war between dark energy's relentless push and gravity's stubborn pull, with three possible finales on the table: heat death, the big crunch, or the most unsettling of all, vacuum decay. Each scenario hinges on dark energy's true nature, a puzzle we're still piecing together with every telescope pointed at the void. First, consider heat death, the universe's slow fade to black. If dark energy remains constant or strengthens over time, expansion will accelerate until galaxies vanish over the cosmic horizon, their light stretched beyond detection. Stars will exhaust their fuel, leaving behind cold cinders. Black holes will leak away via Hawking radiation, dissolving into nothingness over trillions of years. Eventually, even protons might decay, reducing all matter to a thin haze of particles adrift in an ever-cooling void. This isn't fire or ice, but an endless, featureless equilibrium where time loses all meaning, a fate poetically termed the Big Freeze. Then there's the Big Crunch, dark energy's dramatic reversal. If the repulsive force weakens and gravity regains dominance, expansion could slow, halt, and then reverse. Galaxies would merge in a blue-shifted frenzy as space contracts, temperatures soar, and the cosmos collapses back into a singularity. It's the Big Bang in reverse, a cosmic reset button that might spawn a new universe in the aftermath, a cyclical rebirth hinted at in some string theory models. But current data disfavors this scenario. Dark energy shows no signs of fading, and the universe's expansion is still accelerating. Now for the wild card, vacuum decay. The Higgs field, the quantum molasses that gives particles mass, might not be in its true lowest energy state. Like a marble resting in a shallow dent on a hillside, our universe could be metastable, and a random quantum fluctuation or high-energy experiment might knock it into a deeper valley. This would trigger a bubble of true vacuum expanding at light speed, rewriting the laws of physics as it goes. Atoms would disintegrate, forces would unravel, and reality as we know it would cease instantaneously. The chilling part, it could already be happening somewhere beyond our observable horizon, and we'd have no warning before the wave hit. The deciding factor. Dark energy's equation of state, represented by the number W. If W equals exactly -1, heat death is almost certain. If it varies over time, the crunch or even a big rip, where dark energy shreds atoms themselves, becomes possible. Current measurements from projects like the Dark Energy Survey and Euclid Telescope hover close to W equals -1, but with enough uncertainty to keep cosmologists awake at night. This isn't just academic doom-scrolling. The universe's fate shapes the meaning of everything we do. If heat death is inevitable, all complexity and consciousness are temporary flickers against an infinite dark. If the crunch or vacuum decay loom, the cosmos might recycle or reboot, but on timescales so vast, human existence barely registers. Yet there's a strange comfort in knowing that, for now, we're here to ask the question at all. In a cosmos that could end in fire, ice, or oblivion, the fact that we're watching, measuring, and wondering might just be the most miraculous part. From the Great Attractor's hidden pull to the eerie silence of Oumuamua, these 30 mysteries aren't just cosmic curiosities, they're the bleeding edge of human understanding, the places where our maps of reality fray at the edges. Each one forces us to confront how little we truly know. The vast emptiness of the Boötes void whispers that galaxies might not be distributed as we predicted. The Hubble Tension's stubborn numbers suggest our math could be missing something fundamental, and the cold spot, it might be a bruise from a collision with another universe, or just a statistical fluke haunting our telescopes. Then there are the enigmas that hit closer to home. The Pioneer anomaly made us question whether gravity behaves differently in the icy reaches of interstellar space. The wow signal taunts us with the possibility, however slim, that we're not alone, and dark energy, it's not just some abstract force, it's actively deciding the fate of everything, from the fate of galaxies to whether atoms will one day be torn apart in a big rip. But here's the thrilling part: every mystery we solve doesn't just close a door, it opens a hallway lined with new questions. When James Webb spotted those impossibly mature early galaxies, it didn't tidy up cosmic history, it threw the textbook out the window and dared us to write a new one. The multiverse hypothesis didn't simplify reality, it exploded it into infinite permutations, each with its own laws, its own versions of physics, maybe even its own versions of us. So stay curious, because somewhere out there, another Oumuamua is tumbling toward us, another FRB is crackling across the cosmos, another void is hiding in the darkness, waiting to be found. The universe isn't just stranger than we imagine, it's stranger than we can imagine, and the most exciting discoveries aren't the answers we have today, but the puzzles we haven't even thought to ask about yet. Who knows, the next great cosmic revelation might be hiding in data we've already collected, just waiting for someone to look at it the right way, or maybe it's lurking beyond the edge of our observable universe, in the darkness we can't yet see. One thing's certain, the cosmos isn't done surprising us, and neither are we done exploring.